My name is Heather Kulik. I'm an assistant professor in chemical engineering, and my research group focuses on first principles electronic structure methods. We develop these methods and we apply them. Broadly speaking, it's a way in which you solve very complicated fundamental equations on a computer using very high performance computing equipment, and we apply these tools to studying fundamental problems in all forms of catalysis and material science, specifically enzymology, homogeneous and heterogeneous catalysis, and in the discovery and design of new materials. There's been a big transition in the past 10 to 20 years in computational modeling, in that computers are getting faster and faster. So what used to only be applicable to very small scale systems is now becoming applicable to large realistic problems that people care about in either catalysis or materials, or basically any place where we care about chemical reactions or things that are going on, and we want to understand at the nanoscale which atoms are doing what, and these nanoscale properties relate up to macroscale properties. And so the big change that has happened is that the underlying science and equations that need to be solved are very complicated and expensive equations to solve, and people have gotten smarter at how they solve them, how accurate the approximations are that they have to make in order to solve those equations, and computing has changed dramatically over the course of those 10 to 20 years. So before, when you used to be able to study only a handful of atoms, you can now study thousands of atoms with the same level of accuracy. And we focus on catalysis and materials because it's really important to understand at the fundamental level what electrons are doing, what atoms are doing, in order to be able to design a better catalyst, to be able to design materials problems. Fundamentally, we're most interested in understanding how to describe what electrons are doing, what atoms are doing, and how that relates to properties that you care about in the real world, or how it relates to phenomena. And we're interested both in getting smarter and faster at solving those problems on a computer, as well as solving challenging problems where there is a limited understanding. An area in which this is especially important is in transition metal catalysis. So generally, the most interesting and exciting catalysts and materials out there, increasingly with broad applications everywhere, are things that contain transition metals, and those sit in the middle of the periodic table. They have open shells. That means their electrons are available to do exciting things, chemical transformations to value-added products, or just have interesting properties for things like storage, magnetic storage, basically anything. And to understand what those electrons are doing and predict how they will behave is incredibly challenging. So my group's interested both in the side of getting more predictive, because what has held us back from simply designing a catalyst or designing a material on a computer is the accurate and predictive modeling of what those electrons are doing, but then also connecting that to fast screening approaches where we discover things like new nanoparticle precursors, or how catalysts might bind substrates for chemical conversion, 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 chemical conversion.